Hi, and welcome to the section about topological universe on the sheet of graphene. In this section, we're going to discuss about graphene, which is a very interesting material in terms of its physics. But the main reason we are going to use graphene is that graphene is probably the simplest model system that has the right ingredients to understand most of the important concepts that will come up later in topology. So in this section, we are going to cover various aspects of topology and graphene. We're going to start with a talk about the band structure and the symmetries of graphene. This is going to be followed by the description of Landau levels in graphene. We are then going to generalize graphene into the Haldane model, which would give us the first realization of a topological state, what we call the Chern insulator. We are going to then explain the conductivity, the non-trivial conductivity of a Chern insulator. And we will finish this section by discussing a system of twisted bilayer graphene with which we will introduce the concept of fragile topology. So let's start with the first talk, which would be about the energy bands in graphene. So in this talk, we're going to cover a few different concepts. We will discuss the concept of Dirac electrons in solid state. We're going to discuss the concept of a pseudospin. And we are going to discuss what symmetries are responsible for having these Dirac electrons. Specifically, what symmetries we have in the solid state structure of graphene that are in charge of that. Okay, so let's start. So we are going to discuss graphene, but graphene is not a material that you will usually find in nature. In fact, there are other carbon-based materials that are much more abundant and easily to find in nature. These are diamond and graphite. And just by looking on them, you can see that these are very different materials in terms of their property. Diamond is mechanically very, very rigid, very strong. It's transparent and it's a very good electrical insulator, whereas graphite is mechanically very flexible. It's black and it's electrically conducting. The difference between these two materials comes from their different chemical bonding. Carbon has 4 free available electrons, and in diamond, it uses these 4 electrons to bond to 4 nearest carbon atoms in this pyramidal structure. This is what we call an sp3 bonding. So this results in a very strong mechanical structure, but you can see that there are no free electrons available to conduct electricity. Graphite, on the other hand, which is the parent structure for graphene, uses only 3 electrons to bond to 3 atoms in the plane. This leads to an hexagonal planar structure like that. This is called sp2 bonding. So we use 3 electrons. Now there is 1 free electron. This is the pz electron, and this is the electrons that is going to be the focus of the talk. This electron is the electron that is going to conduct electricity, and when we are talking about band structure in graphene, we are going to talk about the band structure of this free electron. So if we take one layer out of graphite, we get this structure of graphene, which overall look hexagonal. In terms of the crystal symmetry, this is a triangular crystal that has 2 equivalent atoms in its unit cell, which we are going to call the A atom and the B atom. We're going to define the lattice constant of this crystal as A here, and the 2 primitive vectors that define the unit cell in this crystal, A1 and A2, are shown here and mathematically written here. Now there are other vectors that are very important for us to remember, and these are the vectors that connect an A atom to its 3 neighboring B atom in the lattice, which we are going to call delta 1, delta 2, delta 3. They are described in these formulas here. So this is the structure in real space. How does it look in K-space? So a triangular lattice in real space has an hexagonal Brillouin zone in K-space. And here the important points to remember are the 2 points at the edges of these Brillouin zones, which we call the K and K prime points, which mathematically are shown here. So now this is the structure. Now we are going to solve the band structure in graphene using the simplest tight binding Hamiltonian approximation of this. And this tight binding is going to capture the most essential facts about the energy bands here. So we are going to use a tight binding that uses only nearest neighbors hopping with an amplitude T. These are operators that create and annihilate electrons at site J and atomic site B or A, only for nearest neighbors. And this Hamiltonian, as you know, it's a periodic Hamiltonian, so its solution happens in K-space. So the best way to get it into a simple form is to go with the operators into K-space. So we can transform the creation and annihilation operator by transform Fourier, and we can even stack them in a vector that includes the annihilation operator of on the A site and on the B sublattice. And if we do this, then the Hamiltonian gets a very, very simple form, which we call the Bloch form, which you can see here. It's just described like a sine of all over different K values of C dagger K, H of K, C of K, where H of K is a 2 by 2 matrix in the basis of the A and B sublattices. And you can see that on this matrix we have only the off-diagonal terms, a sum of e to the ik delta j. And this is coming from the 3 possible tunneling between an A atom and its neighbors. You can see also that on the diagonal here we have 0. And this is because in this model we don't have any direct tunneling between B and B atoms and A atoms. So this is a 2 by 2 Bloch Hamiltonian, and in fact we can write this kind of Hamiltonian in a more generic form that will help us get the solution of this Hamiltonian. And we can see that by remembering that any 2 by 2 unitary matrix we can describe in terms of the Pauli matrices sigma x, sigma y, sigma z, and the unitary matrix, unitary, sigma 0. So if we group the 2 Pauli matrices into a vector which we call sigma, and define a vector function d of k such that its components are 3 functions, dx of k, dy of k, and dz of k, then we can write any generic 2 by 2 Hamiltonian in the following form: d of k vector product with sigma vector, and d0 times sigma 0. And when you write it like this, you can see that a Bloch Hamiltonian like this is nothing else than a mapping between a momentum space, between the Brillouin zone and the 3-dimensional vector space of D. So for every k point in the Brillouin zone, we get an equivalent or corresponding vector in 3-dimensional space. Here I'm plotting the Bloch sphere, but this vector doesn't have to lie on the Bloch sphere. It can have any magnitude. So let's put the Hamiltonian that we derived for graphene in this form. So we had e to the ikx in the off diagonal, which means that we are going to have sigma x and sigma y components. So it's going to give us a dx component, which is sum of 3 cosines. And we are going to have a dy component, which is a sum of 3 sines. And the other 2 components of the vector are going to be 0. And the fact that dz equals 0 is going to be an important part in the physics of graphene. So now that we have the Hamiltonian, let's look on its solution. And let's start with the energy bands, the eigenvalues. So this is the generic solution for the Hamiltonian that we wrote. And in fact, for graphene, we know that these two are 0, so we get a simpler form. And if we plot the energies that we get as function of k, we get a band structure that looks like this, E as function of ky and kx. And we can also plot it as a color map describing one of the bands, the energy on one of the bands, as a function of the Brillouin zone. And when you look on it, there are three important properties that you need to realize. The first one is that we have two bands. This is coming from the fact that we have two atoms per unit cell. The second point is that we have two valleys in K space. You can see it here. This is one valley. We call it the valley around the K point. It's composed of the states here, here, and here. Together they form a single valley. And the states sitting here, here, and here form the valley around the K prime point. These are connected by a reciprocal vector in momentum space, so they are related, but they are not connected to here, so these are two independent valleys. We have two independent valleys not because we have two atoms per unit cell, but because a triangular lattice has a hexagonal Brillouin zone, and this is a property of the hexagonal Brillouin zone. The third property you need to realize is that if you consider neutral graphene, then the chemical potential, the Fermi energy, is exactly at 0. So the physics that would be relevant for us, and it turns out that this is exactly the very interesting physics, is the physics happening around these K points. And here you can see that the dispersion is linear. It's just the dispersion of Dirac fermions. So these are the energy values. Now what about the wave functions? So the wave functions are going to have the usual Bloch component, but now because we have two atoms per unit cell, we need also to define the structure of the wave function inside the unit cell. So we are going to have another internal factor for each k that describes what's the relative weight and phase of the wave function on the A sublattice versus the B sublattice. Generically, for a Bloch Hamiltonian, this is the expression. But if we remember that for graphene dz equals 0, this becomes extremely simplified. And if we divide things here, we can see that this spinor, which we call pseudospin, because it's very similar in many of its properties to regular spin, it's looking like that. And one thing it's important to notice here is that the two components of this pseudospin, in magnitude, they are the same, which means that the wave functions in graphene are sitting, in terms of their magnitude, the same way on the A and the B sublattice. The only degree of freedom that remains free here is this phase, okay, the phase of the pseudospin, which tells us what's the relative phase of the wave function on the A side, N sublattice, as compared to the B sublattice. And this phase is given by this expression. And we can also get what is the phase for every k. This we get from the diagonalization of the matrix, and this is how it looks. I'm plotting the phase as a function of kx and ky for one of the bands. You see that in the center of the band, it's kind of boring. It's a constant phase. But the interesting thing happened where we go close to these k points. You can see that around the k point, the phase, as we go around the k point, the phase gets a 2 pi revolution around this point. And what this tells us is that the Dirac points are singular points, because if we go exactly at the Dirac point, there the phase is not defined. It can be any one of these values. Another thing that you can see here, which is interesting, is that the behavior is exactly opposite in the K and the K prime point. In the K point, we have a vortex of the phase. In the K prime point, we have anti-vortex of the phase. And this is already the first place where you can see that something topological is happening in this band structure, both the singularity and this vortex, anti-vortex behavior, because this shows you that we have singularities that are, as long as they are protected, it's very hard to get rid of. The only way to get rid of this vortex and anti-vortex is to bring them together and make them annihilate, and this is something which is very hard to do. Good, so we described the band structure over the entire Brillouin zone, but since we're interested mostly on the physics near the Dirac points, it's wise to look on small energy scale around the Dirac points and do a linear approximation at a small region around these K points. So we are going to look on momentum, which is the momentum of a K point, plus a small momentum K, such that the magnitude of K is much, much smaller than the magnitude of big K. We are going to start by looking on the K point. So we can take this and take the band structure that we calculated and do a Taylor expansion. So we get the term at the K point plus linear expansion. This is for the dx, same thing for the dy. And you can see that this zeroth order term is exactly zero. This is very easy to see because the sum, when you plug in here the K point, is exactly the sum that gives you the energy at the Dirac point, and we know this is zero. Same thing in this equation. So we are left only with these linear terms, and in these linear terms we have here a sum of vectors, which is very easy to do, and it gives us a vector whose size is square root of 3 over 2a, and it's just the unit vector in the x direction rotated by pi over 3. Here, similarly, we get the unit vector of the y direction rotated by the same angle. So to simplify this more, we can do a basis transformation such that we rotate our definition of the vector by minus pi over 3. We can also define a velocity, a Fermi velocity, which is just like that. And if we do these two, we can see that the Hamiltonian at the K point looks very simple. It's just h bar v Fermi, kx times sigma x plus ky times sigma y. And this is the simple form of a Dirac Hamiltonian. If we do the same analysis, but now for the K prime point, we get almost exactly the same thing, but here, instead of plus, we get a minus sign. And what this shows us is that in the K and the K prime point, there is a different relation between the direction of the momentum and the direction of the pseudospin. If we plot them as vector, and the K vector is rotating clockwise around the K point, then in the K point, the D vector is locked to it. It's rotating exactly clockwise together with the K. On the K prime point, it's going to happen opposite. So if the K rotates clockwise, the pseudospin is going to rotate anti-clockwise. And this is exactly the vortex and anti-vortex structure that we saw earlier. Good. And if we want to group these two equations into a single equation, we can define an index tau z, which takes the value of plus minus 1 for K and K prime. And then we can write both equations like that together. So we see that we have Dirac points, and now the next stage is to understand why do we have Dirac points. And we're going to see that in order to have Dirac points, we must have a symmetry that protects them. So now the next thing we want to discuss is what symmetries we have in graphene. And we're going to talk about discrete symmetries. The first set of discrete symmetries are symmetries that happen in space, spatial symmetries. And the ones we are going to discuss are inversion symmetry and C2 symmetry. Inversion means that you take a point in real space, x, y, z, and reflect it into its corresponding point, minus x, minus y, minus z. C2 symmetry, and when I say C2 symmetry, I mean C2z, is a symmetry that rotates the system by 180 degrees around the z-axis. These are, in general, two different symmetries because they act on the z-axis differently. But in the case of a two-dimensional layer for which z-axis is not relevant, these two symmetries are equivalent. So I'm going to interchange between these two as we go. So just by looking on this, you can see that this structure has inversion symmetry if we pick the right points around which we perform the inversion symmetry. So for example, if we look around the center of the unit cell, you can see that if we flip, we get exactly the same crystal, only that we need to take a B atom into an A atom and an A atom into a B atom. So formally, this means that if I is the inversion operator, then the action of the inversion operator would take an operator annihilating an electron at a J site and the A sublattice and transform it into an operator annihilating an electron and the minus J site on the B sublattice, and vice versa here. Now, if we group these two operators in a vector form like we did earlier, then we can write it even simpler. We can see that the inversion operator operating on this vector of operators is just sigma x times c to the minus j. So we invert the coordinate, but we also operate with sigma x, which means that we flip between the A and B atoms. So this is in real space. Now, how does it look in K space? It's very easy. We can just do the transform Fourier here. And we can see here that the I acts on the real space operator. We can take it from here. And you can easily see that this gives you sigma x times c to the minus k. And this is very simple to understand. Inversion take a vector k and also inverses it to a vector minus k. So now we want to ask what Hamiltonians will have inversion symmetry. So these Hamiltonians are the ones that are going to commute with the inversion operator. So what does it mean? It means that Hamiltonian should, if we put the inversion operator here, we see that we get this expression. And if we operate with what we saw here, then you can see that we get sigma x h to the minus k h sigma x. And we know that this has to be equal h if the Hamiltonian is to be inversion symmetric. And this will happen only if for every value of k, these two terms would be equal. Okay, so let me recap this. If for every k, h of k equals sigma x, h of minus k, sigma x, this means that our Hamiltonian, our Bloch Hamiltonian, is inversion symmetric. So this equation puts some constraint on the d vectors that are allowed. We can, for example, look on the x component, the component that is the coefficient of the sigma x, and you see that if we place here sigma x, we get sigma x times sigma x times sigma x, which equals sigma x. So this equation just becomes the equation that requires that dx of k equals dx of minus k. This would be different if we do it for sigma y, because sigma y anticommutes with sigma x, and then we'll get a minus sign here. Same thing for dz, and for d0 we'll get it without a minus sign. So you see that we get a set of requirements of the vectors that define our Hamiltonian. And if we plot it in a graphic form, what it says that if we know what is the d vector that correspond to the k point minus k, we have to have a specific d vector that correspond to the point k that is related to this d vector by this relation. So it's basically a constraint that connects the two d vectors that correspond to k and minus k. Now let's see if this is valid at all to graphene. Does graphene has inversion symmetry? So we saw that graphene Hamiltonian is described by the dx as just a sum of cosine terms. The dy is just a sum of sine terms, and the dz equals 0. And now you can see that because cosine is a symmetric function in k, it obeys exactly this equation. Sine is an antisymmetric function in k, it obeys this equation. And 0 trivially obeys this equation. So indeed, graphene has inversion symmetry. So this is the first symmetry we discussed. Now let's talk about a different discrete symmetry, which is time reversal symmetry. Spinless time reversal symmetry. And spinless time reversal symmetry is formally just the complex conjugation operator, which take the imaginary I and flip its sign. So if we operate with the time reversal symmetry on a local operator, it just keeps it intact. But if we operate on an operator with well-defined momentum, it flips the momentum. This is just because in the e to the ikx, we flip the sign of the I. And this is very intuitive. An electron going in the k direction, if we look on it back in time, would go in the opposite minus k direction. So if we require the Hamiltonian to commute with the time reversal operator, then similar to the analysis we showed before, we get a different kind of requirement on the Hamiltonian. This time it would be that h of k equals the complex conjugate of h at minus k. So this would give us a different constraint on the v vector, which you see here below. The difference between what we saw earlier and now is that now we don't have a minus sign for dz. Okay, so graphically now this would lead to this relation. So now we want to ask which one of these symmetry is responsible for the fact that we have a Dirac point in graphene. And why do we even need to resort to symmetries as a source that gives the Dirac point? Well, in 2D, Dirac point is not something generic. It's something that's fine-tuned. And the only way to get a Dirac point that is fixed is that we have some symmetry that protects it. And we want to find what this symmetry is. So is it inversion symmetry? So you can see what does inversion symmetry does. It gives you some constraint about between the Hamiltonian that is at k point to the Hamiltonian at minus k point. This is not good enough. This is not going to help us to protect the Dirac point. Time reversal symmetry is the same. It's not going to give us a constraint on a certain term in the Hamiltonian. It's just going to give us a relation between two terms. But what happens if we say that our system has both these symmetries? Okay, then we can do something nice. Because you can see that if we apply the first symmetry, it tells us that if we have for the minus k this d vector, then for the plus k, we must have this d vector that reflects this symmetry. But now, let's say that we have for the plus k this d vector, and we apply the time reversal symmetry. It tells us that for the minus k, we should have this d vector. Okay, so if we have both these symmetries together, it means that we now have a stronger constraint now on a specific k point in space. So it tells us that the minus k that has this vector to begin with, after these two symmetries, should also have this d vector. And of course, the d vector at the k point has to be singular value. which means that this has to be equal this. So what kind of constraint does this give us? You see that on the x and y components of the d vector, it doesn't give us much. Because you see that these two vectors by construction have exactly the same x and y components, so there is no constraint. But on the z component, you see that it says something very strong, because for this vector to be equal to that vector, this is going to happen only when dz equals 0. So the combination of these two symmetries, C2 and T, in fact directly says that dz equals 0. The coefficient of the sigma z component equals 0. And this is exactly the term that is responsible for the fact that we have Dirac points. This is saying that on the diagonal we don't have terms. It's 0, and this is what is responsible for having Dirac points. What it also means is that if we break C2T symmetry, the Dirac points are no longer protected. So we can break either of these symmetries and break the Dirac points. So let's take the simplest example, which is also a realistic example. And this is to break the inversion symmetry, or the C2 symmetry. And this is realistic because we often get it in real-life systems. When we put graphene on another substrate, typically it's a hexagonal boron nitride, which has the same crystal structure, hexagonal crystal structure as graphene, but instead of having two carbon atoms, which are equivalent, it has two inequivalent atoms, boron and nitride. So if we put graphene on top of this substrate, now we break inversion symmetry. You can just see it by trying to flip this picture on in the head. But you can see that now the A atom is sitting on boron, and the B atom is sitting on nitrogen, and these are not equivalent anymore. So what this does is that it changes the relative energies of the A sublattice with respect to the B sublattice. And it exactly is going to introduce this sigma z term that we didn't have before. So we are going to have delta for the A sublattice and minus delta for the B sublattice. And this introduces a dz term whose magnitude is delta. How is it going to change the band structure? Well, it's going to open an energy gap at the Dirac point, which looks like this. Formally, the energy structure is going to look like this. We have this extra term plus delta squared. And this is opening a gap whose magnitude is 2 delta. Okay? And when we are opening a gap, we're taking graphene that used to be a Dirac conductor into a semiconductor with a gap, and with electrons acquiring an effective mass. What is the mass in this model? Well, it's very easy to connect it into the gap parameter. And you can see that the mass is just delta over V Fermi square. An easy way to remember this is that this is just like E equal mc squared, only that we replaced here the speed of light by V Fermi. So you can see that by breaking inversion symmetry, we introduced a mass term that opened the gap and turned Dirac electrons into graphene into a massive semiconductors. This gap is the starting point for us to consider topological properties. It's going to introduce an interesting geometrical phase and geometrical curvature, the Berry phase and the Berry curvature, which we are going to talk about in subsequent talks. But this alone is not going to turn the material topological. What we will see in 2 talks, that if we add another gap term, another mass, that behaves slightly different with a slight trick that is introduced in the Haldane model, then we can create masses with different signs, and then we can turn a band structure like this, which is a trivial semiconductor, into a band structure of something which is topological.